Hello. So this video, we're just going to be introducing the idea of what a polynomial is. So we're going to talk about sort of what it actually sort of is in terms of like the actual terminology and how we refer to them and some little bits of history with it as well. Okay, so say we have some number, x. Now, sort of a natural thing to think about, like way before even sort of math was really a thing people thought about, right? When you're keeping track of cattle or whatever. You might have some number of cattle, or you might have some sort of number of grain per cattle you have to keep track of or something. So one of the sort of obvious things to do would be to add this thing to itself a bunch of times, as well as multiplying this thing against itself, right? So if we have some starting value, we multiply it by some, like itself by some number of times, however many you want, let's say n number of times, right? So we could have x to the n. So this thing sort of represents a somewhat natural thing to think of, right? So if you have the number 5, you just multiply it against itself a bunch of times, okay? Likewise, we can add x to itself some number of times. We could call that, say, a, right? So if we have 5, we could add 5 to itself a bunch of times, say some a number of times, and that's how you get ax to the n. So polynomials are sort of one of the very first functions that we would naturally run into just playing around with numbers and being, nerds with it. As it happens, they turn out to be very useful for a number of reasons, some of which are sort of deep magic in mathematics, but they make a great sort of playground for new concepts. For that reason, it's worth a mention here that the polynomial sort of section of any class tends to be much longer than other sections, by virtue of the fact that it's sort of where we introduce a lot of concepts that apply also in other functions. So this is something we're going to run into in the future, just to put it sort of on your radar now. Nonetheless, as it might suggest, we're looking mostly at terminology right now. So if we want to look at ax to the n, right, this idea of having both the addition n, the power bit, this thing we call a monomial. Originally, it was actually a mononomial, but it turns out people suck at writing stuff the same way all the time. And over time, people sort of ended up shortening it to that monomial. And the reason I mention this is because it makes it sort of easier to remember if you think of mononomial, because mono means one, nomial is name, and so it's one named thing, right? It's one term. Now, as a sort of note, we do want to make a little bit of a restriction here. In particular, we want to sort of restrict our case to when we're using whole number powers and sort of non-negative ones, right? So in particular, we want n to be sort of a natural number or 0. So 0, 1, 2, 3, 4, whatever. Likewise, a could be any sort of typical number or what we would call a real number. Okay, so the coefficient could be really anything. Square root of 2, pi, e, 5, negative 17, all perfectly fine for a. But n has to be a whole number and a not negative number. So 0, 1, 2, 3, etc. Okay. Now, if we connect more than one monomial, these things get their own names because they come up a lot. So in particular, we have binomials. Bi meaning two, nomial, still name, so two named things, two terms. And the other sort of one that we run into enough that we actually use its name is the trinomial. So that's if we have three terms, right? Tri, three, nomial, name. So these are sort of the classic ones. It does keep going if you wanted to keep sort of going with that, but nobody actually uses those. It's really 1, 2, 3, many. That's really how we roll. And so in that sort of spirit, if you have a whole bunch of these things added together, we sort of just generally call it polynomial. Poly for many, and again, nomial for name, many named things. Now, strictly speaking, as a note here, we can actually call monomials and binomials polynomials. It's sort of a shorthand because we're thinking of polynomials as like the general thing. But it would not be correct to call, say, a binomial a monomial, right? So we really want to think of it sort of as polynomials, the big umbrella, and then we have these sort of subtypes that we are specifically sort of referring to be very clear about the number of terms we care about, okay? All right. So the problem here is if we sort of add a bunch of these things together, right? If we have these n number of terms that we're going to add together, we can think of all the other terms, right? So we have n, n minus 1, n minus 2, all the way down to 2, 1, whatever. So if we had, say, n is 4, we would have x to the 4th, x to the 3rd, x squared, x to the 1, x to the 0, whatever. Now, this is fine if we have 4 or 5, right? But it could be 5, it could be 10, it could be 20. It could be a very large number. And in fact, this sort of makes an issue when we start trying to think about the coefficients, right? Because we want to be able to refer to a specific coefficient. And if we have 5 or 10 or 20, we could do sort of our classic alphabet, right? Ax to the n, that's the first one. B would be the next, right? The second biggest coefficient in terms of the degree. C could be the third coefficient, down to however many we have. Life is good, right? So if we have 5 or 10 or something, we could do that. Might get a little unwieldy around 20, but it would still technically work. What about 500? Right, that is a possibility. We might have 500 of these terms, or more, a computer might have 500 of these terms. And then suddenly, ABC isn't going to fly, right? Even if we wanted to drag in other alphabets and be like, all right, let's use the Greek alphabet and the Hebrew alphabet and Cyrillic, and we're still not going to have enough to get 500 different letters. Moreover, it gets very confusing if you're going to use a bunch of different alphabets as to which one goes to which, right? Okay, is beta the second letter after the third alphabet, which would make it the coefficient to the 87th letter? Nobody wants to do that, right? So we have sort of two problems here. We need some naming convention that will give us the coefficient in a way that, one, it doesn't matter how many terms we have. We could have 5, 10, or 200. It would still work. And two, we need to know sort of which x power it's associated with, right? If I give you a name for a coefficient, you should be in your head able to be like, that's the coefficient to the x to the 27th power or something like this, okay? So the standard that we have sort of gone into now, the sort of standard way of notating this, is to use subscripts. So in particular, remember we had a x to the n, so we're still going to use a, but now we're going to do an a with a subscript that, notice, matches the power of x. So a sub n goes to x sub n. A sub n minus 1 goes to x sub n minus 1. A sub 2 goes to x to the 2, or x squared, right? And this is useful because it's just a number, right? So if I have 500, that would just be a sub 500. And if I said, okay, what's the coefficient to x to the 38th power, it would be a subscript 38, right? It would just match whatever that power is, okay? So this is sort of a nice way of keeping track of these things, with the slight note that in its standard form, we usually don't bother writing this x to the 0, right? This is not incorrect, but x to the 0 is just 1, so we don't really need it because multiplying by 1 doesn't change the value. So typically we just end with a sub 0, and we just sort of understand that that's attached to this x sub 0, or x to the power of 0 that we don't really need to worry about. Okay, so this whole sort of monster of a thing here is the standard form of a polynomial, okay? So when we talk about sort of in the cases where we need a generic polynomial, we are going to write it in this way with this a sub n, x to the n, a sub n minus 1, x to the n minus 1, right? These sort of systematic pieces, and then some tail that sort of ends at a sub 0 or whatever. Okay, and the point that it's trying to get across is that it doesn't matter what the degree is. It could be 3, 50, 8,000, 1. Any degree is fine. That's what this sort of format is meant to mean. Okay. Now, there's a couple things that we want to also know in terms of terminology from this. So this first term, and I'm sort of being misleading by saying that. Really what I mean is the term with the highest degree or the highest power. That is our leading term, and it is typically written first, hence the word leading for leading term. But it's not always written first. So we care about this term because the polynomial sort of eventually behaves. I realize those are very sort of hand-wavy terms that we're going to dive into later, but it sort of eventually behaves like the monomial that is the leading term. So the leading term, in some sense, dictates a lot of the sort of eventual behavior of the polynomial and thus can be very useful. it doesn't tell us much necessarily about the short-term behavior. And again, what we mean by these terms is something we're going to explore in other sections, but this sort of motivates why we care about the leading term specifically. Also, the leading term sort of pulls out some other information for us. So one, the leading coefficient. Leading coefficient does some important things with how the function sort of behaves and looks, and some other pieces that, again, we'll dive in specifically where that sort of comes up as we go. And the degree of the polynomial. So the degree of the polynomial is just the power of the leading term, which, remember, is not necessarily the first term, but is the term with the highest power. So the degree of the polynomial is effectively whatever the highest power is of all of the x terms in that polynomial. Okay? So we can see, right, the leading term is attached to the has the leading coefficient attached to it and has the degree of the polynomial attached to it, all sort of wrapped up in one. Now, I'm being careful about sort of distinguishing between first versus leading term. And that's because a lot of the times, for whatever reason, people will sort of give you these things out of order, which is frustrating. So a good sort of first step whenever you're dealing with a polynomial, almost regardless of what you want to do with it, is to take something like what you're handed, right? See, we have 3x squared, 2x to the 1, minus 16x to the 5th, which is the biggest power, plus 7. It's helpful to rewrite this so that you have descending value of the power, meaning like go from the highest power to the lowest power. So in this case, we'd move the minus 16x to the 5th to the front, and then have the next lowest, and so on, okay? So here, our leading term then, after we've rearranged it, is going to end up being the first term. But to be clear again, beating a dead horse, I know, but it is the term with the highest degree. So here it's negative 16x to the 5th. The leading coefficient is the coefficient of that term, right? The number in front, so that's just negative 16. And the degree of the polynomial, which is the degree of the leading term, is 5. Okay, so the leading term has everything in it. Leading coefficient is just the number in front, and the degree is just the power of that leading term. Okay? All right, so what do? We introduce the idea of polynomials, right? They're sort of a natural first function to think of because it's just playing around with a number, multiplying it by itself, adding it to itself, sort of obvious things to try to do. But it turns out that they sort of are a nice play function. They're a nice sort of function to use as a starting point for ideas of functions in general. As a result, polynomials tend to have sort of a lot of stuff associated to them because we use that as the sort of starting place for general function ideas that then we sort of use in other functions as well. So an example of this is factoring. Factoring is done a whole lot with polynomials, and it still applies to other functions. It's just sort of nicest to see in polynomials. We also did some terminology, right? Degree of the polynomial, leading term, leading coefficient, these things that are sort of, I am telling you at the moment, but we haven't done it yet, I am assuring you that these things are going to have some sort of importance about understanding how the function behaves. That's something that we're going to see in the future in various other contexts. Okay? So that is that.